Modeling relational data in a NoSQL database like Firestore can be a challenge, especially if you come from a SQL background, because you'll have to unlearn many of the principles that you already know. My goal today is to show you a handful of techniques that you can use to model data relationships, such as one-to-one, one-to-many, and many-to-many. Because NoSQL is schemaless, we have the flexibility to model these relationships in a variety of different ways. I'm going to show you how to build these data models in the Firestore console, and we'll talk about the trade-offs for each technique. If you're new here, make sure to like and subscribe, and follow along with the source code at angularfirebase.com. Firestore is a NoSQL document-oriented database, similar to CouchDB and MongoDB if you're familiar with those. Instead of storing data with a bunch of columns and rows like you would with a traditional SQL database, you store data as collections of documents. Collections don't store any data of their own, they're just containers to hold multiple documents that you can query. And a document itself can just be thought of as a JSON object. In order to keep your queries efficient, it's important that you make your collections large and your documents small. In fact, documents need to be at least 1 megabyte or smaller. But a collection can hold millions of documents and still be queried efficiently. Firestore gives you 3 fundamental ways to model your data. The first way would be a root collection, which is just a collection of documents in the root of your database. The second option is to embed data directly on the document itself. It behaves very similar to JSON, so we can save objects, arrays, and other data types on the document. It just needs to be relatively small, again limited to 1 megabyte. Then our third option is to nest a sub-collection on a document. This allows us to scope collections to a parent document, creating a hierarchy structure. Now that we know the fundamentals, let's jump into the Firestore console and start modeling some data. The first thing we'll do is create a root collection called users that maintains a document for each user in our app. Every document in a collection needs to have a unique ID, but you can create your own ID, and there are some clever things you can do to manage relationships by doing that, which we'll get into here in a second. Now let's assume that every user in our app might be able to obtain certain rankings or achievements through activity that they perform in our app. In other words, a user has many rankings. The easiest way to maintain this relationship is by embedding an object on the document itself. So we'll call that rankings and select an object. And then for each relationship, we set a key and a value. You can make queries based on these object properties, so it's important to use consistent naming across all user documents. I'm just using a number as the value, but you could nest an additional object or other data type under each property. That works pretty well, but it doesn't scale if your anticipated data footprint is any greater than a megabyte. So embedded data works best when you have a small, simple data structure that doesn't need to scale up to thousands of records. Let's go ahead and assume our ranking data is much more complex, and we'll nest it as a sub-collection. We can click Add Collection, which we'll call Rankings. Then we'll quickly add a couple of documents to this sub-collection. The nice thing here is that we can save as many documents in this collection as we need. And it also maintains the relationship with the parent document, which happens to be the user. That's great for representing the relationship, but you need to ask yourself, are you going to need to query this data across any parent documents? In other words, do you need to make a query that goes something like, I need all users that are ranked black belt? Because currently that type of query is not possible in a sub-collection. The data is completely scoped to that user, so you can't use it to query across multiple users. So what we're going to need to do in that case is denormalize our data and save our rankings collection as a root collection. When we create a document in this root collection, we'll want to save the user ID of the associated user on each individual document. You can embed a document ID as a string or the actual full path to a document in Firestore. In most cases, saving the document ID as a string will be sufficient, but there may be cases where you have deeply nested complex data that would benefit from having the full document reference. In either case, the idea is very similar to a foreign key in a SQL database. We can't do join queries like we do in a SQL database, but what we can do is reference a related document and pull that in as a secondary query. With the root collection, we can also reference multiple user IDs to create a many-to-many relationship. By adding a second user ID, what I'm doing here is creating a relationship that says a ranking can have many users and users can have many rankings. Now let's try another example. Let's see if we can model the relationship between tweets and users in Twitter in Firestore. So the first thing I might do is create a sub-collection of tweets under each user document. A tweet is owned by a user, so logically you would think that a tweet should be nested under the user. When displaying tweets for a given user's feed, that should be perfectly fine. But the one caveat there is that if we want to display a feed that goes across multiple users, we're going to have a problem. Every query to this tweets collection is going to be scoped to that user document. So let's imagine we want all of a user's tweets for a certain day. We could say where created at is greater than or equal to today. That works well in certain cases, but in this case, since we want to query all of the tweets across all users, we're going to need to make this a root collection. That will allow us to modify our query to be scoped at the root instead of underneath this user document. We could also try to embed a tweets object on the user document directly, but since our users can potentially have thousands of tweets, that doesn't really make sense from a scaling standpoint. So we'll go ahead and move that collection to the root, and this time we'll save the user ID on each individual tweet document. We lose the convenient relational structure of a subcollection, but in return we get a more flexible structure for compound queries. Now we can write code that's going to return all the tweets for multiple users, for example, all the tweets created today. But we can still scope the tweets to the exact user by querying that user ID. So we'll say ref where user ID equals user1. And we can even chain these where statements together to perform a compound query. So that gives us a nice one-to-many relationship between users and tweets, but users can also like other users' tweets, so how might we set that up? That gives us a many-to-many relationship where a heart belongs to both a user and a tweet. And we also want that relationship to be unique. For example, a user shouldn't be able to heart the same post multiple times. So one easy way to enforce that uniqueness is to create your own custom document ID. So in this example, I have a heart document where the ID is the user ID followed by an underscore followed by the tweet ID. By doing that, it becomes easy to query a specific tweet to see if a user has already hearted that tweet. And it also ensures that a user can't heart a tweet more than once. If you have a SQL background, this technique is very similar to using an intermediate table for joins. If we have a user ID and a tweet ID in our front-end app, we can simply use those to request the corresponding document to see if the user has already liked a tweet. Then we could get the total heart count by querying the hearts collection with that tweet ID, but this does pose one major problem. If a tweet has been liked thousands or millions of times, we're going to have to query that entire collection just to get a simple count. To overcome that problem, what we want to do is aggregate our data as it's created. That just means we sum up the total hearts every time a new one is created and save it on the tweet document in the background using Firebase Cloud Functions. It's surprisingly simple, and I show you exactly how to do it in episode 63. But the general idea is that we're going to need to show the heart count on a tweet very often, and we don't want to read that entire collection over and over again. So we set up a cloud function that runs whenever a new heart document is created. Then we reference that tweet and increment or decrement its total heart count. That allows us to perform a single document read when showing that count in the front end, which is going to be a lot faster, less expensive, and it's the only way you can scale. I'm going to go ahead and wrap up there. If you're a pro member, be looking out for a more advanced data modeling video in a couple days to answer some of the questions that you posted on Slack. I hope this video gave you some basic ideas on how you can model relationships in Firestore. If it helped you, please like and subscribe. And if you want to get my advice for modeling your own complex data structures, consider becoming a pro member and drop me a line on Slack. You'll get a free copy of my book as well as one-on-one project support. Thanks for watching, and I'll see you soon.